A capacitor is a device that stores charge. If we connect a charged capacitor to some other electric device, we can use this charge stored to power that device. The question now becomes, how much energy can we store in this way? To answer this question, we first have to look at the relationship between the charge stored on a capacitor and the potential difference that exists between the plates of the capacitor. This is just a linear relationship where the constant of proportionality is the capacitance of the capacitor itself. We now ask the question, if we've got a certain amount of charge already stored on the capacitor, how much energy does it take to remove a tiny amount of negative charge from the positive plate and to add a tiny amount of negative charge to the negative plate? Therefore, if we look on our graph, we're asking how much energy does it cost to charge or to increase the charge stored on the capacitor by an infinitesimally small amount, dq. To calculate this quantity, first let's look at the change in potential energy that the positive plate experiences if we remove a small amount of negative charge from it. The positive charge stored on the capacitor, on this plate of the capacitor, therefore increases by a small amount dq. And from the definition of the electric potential, we know that the potential energy of the positive plate now becomes just the electric potential of the plate times the small amount of charge, positive charge dq that we've added to this plate. For the negative plate, its potential energy becomes the negative potential, electric potential of this plate, times the negative amount of charge we added to it. We can now calculate the change in potential energy that we incur if we remove a bit of negative charge from the positive plate and add a bit of negative charge to the negative plate. This is just equals to the potential difference between the two plates times the small amount of charge dq that we are removing on the one side and adding on the other. This also has to be equals to the amount of work that we are doing in removing the charge from the positive plate and adding a negative amount of charge to the negative plate. Note that we are making no statement as to the path or how we take one bit of charge from the positive plate and add another to the negative charge plate. We are purely looking at the initial and final states of these plates. Knowing the tiny amount of work that needs to be done to remove a tiny amount of negative charge from the positive plate and to add this same amount of negative charge to the negative plate allows us to simplify this expression by substituting in for the potential difference the charge stored at that instant on the capacitor divided by its capacitance. In order to calculate the total amount of work done, in order to charge a capacitor from initially having zero charge to having some charge Q final, we must now calculate the integral of the work done, as is shown on the bottom of the screen. We note that the capacitance is a constant, as we have shown in an earlier slide, that the capacitance of a capacitor only depends on the geometry of the capacitor itself. Therefore, this is a relatively simple integral to solve. It's the integral of q dq, which evaluates to this expression, which now gives us the amount of energy that we can store in a capacitor if we know the amount of charge it carries.